Okay, so today we have Oleg Chalykh, who will tell us about elliptic crystallographic Calogero Moser systems as Seiberg Witten integrable systems. Take it away.
Okay, thanks very much for the invitation. This is based on joint work with Philip Argyres and Yongchao, and I should tell straight away that I'm not a physicist. So if you have any questions on the physics side, I'm happy that Philip is here. So you should ask him rather than myself. Okay, so there are a couple of papers already, and there is some further work in progress. So let me explain my plan. So I will just as a motivation, I will just give some background on these crystallographic reflection groups and Calogero Moser systems. Then mostly I will talk about rank 1 case, and so this is related to elliptic curves with symmetries and the relevant Cherednik algebras. And then I will talk about the Lax matrices for these integral systems, and which have some peculiar duality properties. And then I will move on to the spectral curves for these integrable systems, which lead to some elliptic pencils or elliptic surfaces, which then can be seen related to some of the superconformal field theories. And if time permits, I should say a few words about the quantum spectral curves, and then about the higher rank case as well towards the end. Okay, so let me give you some background on first on these complex crystallographic reflection groups. So we will be in the following situation. We consider X to be an abelian variety and dimensional abelian variety, quotient of Cn by a lattice, and W will be a finite group generated by complex reflections acting on this abelian variety. So in other words, the action of W preserves the lattice. Now, so then you can form the semi-direct product of this finite group and the lattice. This is an example of what people call a complex crystallographic group. And well, crystallographic because it has a lattice inside, and complex crystallographic because it's more general than real crystallographic. For the real crystallographic groups, W will be just a real reflection group preserving the lattice. And the lattice for the usual crystallographic group would be just a rank n in real space. And here the lattice should be a full rank 2n, so integer lattice of rank 2n. So the quotient is compact. So this group, infinite group, can be generated by reflections, complex reflections. So we call an element a reflection if it fixes a hyperplane. If this element has a finite order, then in the complement to the hyperplane, it acts as a cyclic, by roots of unity as a cyclic group. So, so in a suitable basis, this any reflection has lots of ones along the diagonal, and then some roots of unity in one place. Okay, so this group is generated by reflections. It's not difficult to see because W was generated by reflection. That's part of the definition. And Popov actually gave a full classification of all such complex crystallographic reflection groups. And it's a long list, but the relevance to us is that for each of these groups there is an integrable system, interesting integrable system behind. So these were constructed by Etingof, Felder, and Veselov in 2011. And so this integrable system is living on the cotangent bundle to X, to our abelian variety. And in the classical case, we are talking about n Poisson commuting Hamiltonians. There is also a quantum version when we have n quantum Hamiltonians commuting. And well-known example is related to actually to real crystallographic groups. So that was the background for the work of Etingof, Felder, and Veselov. So if you consider just real crystallographic group of AN, BN, and so on type, then you, as your abelian variety, you take the quotient of Cn by the, so you take the usual root lattice and then you double it by using this complex modular parameter tau. So is usually imaginary part of tau is positive, so you make this into a lattice of full rank 2n, and as an abelian variety, actually this is just a direct product of n copies of an elliptic curve with this parameter tau. But it has a natural action of the wild group on it because the lattice is a root lattice, and so in that case, this integrable system, which in general I will refer to as elliptic crystallographic Calogero Moser system. In this special case of a real reflection group, this is just what is known as just elliptic Calogero Moser system of type W. W refers to the wild group. And by the way, if at any point there are any questions, please feel free to interrupt me and ask. So the particularly well-known example is the Calogero Moser system. So this is ECM, elliptic Calogero Moser system. I will use this abbreviation and sometimes. So type A is particularly well-known. So it has n commuting Hamiltonians, and the first one, it's just the sum of momenta and variables. So I'm having here n of p variables, n of q's, q oppositions, and the second Hamiltonian is what you would like to have in the kind of physically relevant system. There is a kind of quadratic, it is quadratic in momenta, and this is like potential term, which shows that there are interactions between, this, you can think of these QIs as particles on the line, and the interaction is given by Weierstrass P function like this, and this parameter G squared, it's a coupling constant parameter. It's like strengths of interactions. And it is well known, especially, I guess, to all of you, that this is, okay, there are some higher Hamiltonians which are more difficult to write down explicitly, but nevertheless, they exist. And this integral system was recognized by Denage and Witten as Seiberg Witten integral system for a certain supersymmetric gauge theory, with SUN as a gauge group. And later, Hocker and Fong, they realized also elliptic Calogero Moser system for other real reflection groups as certain Seiberg Witten integral systems.
Should this be the type AN-1 in the sense that
yes, correct.
Yeah, right. So you usually set H1 to 0, basically. And
well, you don't have to.
You don't have to.
Yes, but from the point of view of integrable systems, you don't have to. But yes, so type A and yes, that's correct. So it should be N-1. Thank you. And so in general, this after discovery of these Seiberg Witten integral systems, the general problem is to find a suitable integral system behind each given for Dn equals to quantum field theory, and this I can skip. This is background of the geometry behind that. I'm sure all of you Nowadays, so two main overlapping sources. Two sources of Seiberg Witten integrable systems are as follows. So one source is n-particle integrable systems, like Toda system, spin chains, this elliptic Calogero Moser system, and others. And another source are Hitchin systems typically on puncture-driven surfaces. And sometimes integrable system actually can be interpreted both ways. And this is actually our case. So our proposal is that these complex crystallographic Calogero Moser systems are a good source of Seiberg Witten integrable systems. And so far in the cases we have worked out, they can be interpreted as a Calogero Moser system, but also as a Hitchin systems on the punctured sphere. So I will talk about that later. So let me just give you a little bit of general background for these integrable systems. In general, they're quite complicated and not so explicit, but so here we're in the same situation as before. We have a finite complex reflection group acting on the abelian variety. And then, of course, there would be some fixed points for this action of W. So so it's like mirrors for reflections. So this will be some kind of reflection hypertori in our abelian variety. And so the integrable system, actually, the Hamiltonians will have poles at this reflection, at these mirrors. So it's like in the example we saw before. We had this Calogero Moser system, which potential actually was singular, had second order poles when particles collide. Yes, so I'm just using this notation for the part of my abelian variety where the group W acts freely. So I remove all fixed points, which is a union of hypertori. And then I consider cotangent bundle to this to X with standard canonical coordinates. So Q is coordinate on X, P is in the cotangent bundle direction. And the Hamiltonians of my integral system will be W invariant functions on this cotangent bundle. So I'm a little bit careful here, taking not the whole X, but just the regular part. Because as I said, they have poles. And each Hamiltonian will have a leading term at constant in momenta. And so this leading polynomial in momenta would be, actually this will be generators of the ring of W invariant polynomials in momenta. And so the degrees of these Hamiltonians or degrees of these polynomials, the leading terms, are dictated by the group W. So, okay, and dots here indicate some lower order terms, fairly complicated, and they depend on the additional parameters of deformation. So it's not just one integrable system, it's a family of integrable system depending on several parameters. And these deformation parameters, if you set them to 0, then there is nothing here in this part, in the dot part. So the Hamiltonians are just functions of momenta. So this is like a free motion in the cotangent bundle, linear motion. So the number of these parameters of deformation, it's a bit complicated, but essentially they're assigned to each reflection hypertorus. You assign these parameters, complex parameters, which I call CHI. So the number of them, so the index I is between 0 and so M, which I call MH here, is the, so remember the reflection hyperplane or hypertorus will be stabilized by some cyclic group of some order, which I call MH. So the stabilizer of the hyperplane is a cyclic group of this order, and so you have that many parameters. So mh minus 1 parameters. So for example, if it's reflection of order 2, which fixes these hypertorus, then there is just one parameter. If it's complex reflection of order 3, 2 parameters, and so
Could I interject a comment, just translating this into physics terms, so it might be more familiar to some people in the audience. So if you turn off the deformation parameters, are what we would call mass parameters from the point of view of a Coulomb branch geometry for n equals 2. And if you turn them off, what he was saying is that the Coulomb branch geometry will look like a complex reflection group orbifold, which people often associate with these n equals 3 Coulomb branches. But these are more general in the sense that there are many more deformation parameters that you can turn on. So they correspond to a whole set of other possible consistent Coulomb branch geometries. Anyway, I thought that. Okay.
Thank you. Right. Okay. So yes. So these are mass parameters, as Philip says. Yes. And overall requirement is that you need to prescribe them in the symmetric way, symmetric fashion. So if you have two hypertori which are related by the action of the group, then the parameters should be the same. So effectively, parameters are assigned not to a particular hypertorus, but the whole W orbit of these hypertorus. And yes, and the Hamiltonians, because they are W invariant function, effectively, yes, integral system is not just on cotangent bundle to X, but on the quotient of that by W. That's the orbifold which Philip mentioned. Okay. Yes. So far we have worked out the connection to quantum field theory in the following cases. So when the W is what people call a Riesz product of the symmetric group Sn and the mth root of unity. So this group, alternatively, you can think of that as a semi-direct product of symmetric group and copies of the roots of unity, Zm, and this group naturally acts on the following abelian variety X, which is just n copies, product of n copies of elliptic curve E, where this elliptic curve should allow action of the roots of unity. And so it's elliptic curve with symmetry, and symmetry can be only of this order 2, 3, 4, or 6. And the group W like that acts. So symmetric group clearly just swaps the factors, the curves, and roots of unity. Each group of roots of unity acts in the corresponding factor by the symmetry of the elliptic curve. Okay, so what happens is that these integrable systems corresponding to this case, they can be thought of as Seiberg Witten integrable systems. When M is 2, it's SQFT with gauge group USP2N. So the mass parameters, there will be 4 mass parameters, and in rank 1, 5 mass parameters in higher rank, plus in addition there will be a modular parameter for the elliptic curve in this case. And the other case is M equals 3, 4, and 6. So you need special elliptic curves with that symmetry. So the modular parameter would be fixed. It's no longer arbitrary. And but the mass parameters, the number of mass parameters in this case is 6, 7, or 8 in rank 1. And plus 1 extra parameter in high rank. I think physicists call that anti-symmetric mass, if I'm correct, this extra parameter which appears in high rank. Okay, so So these cases we discovered they are related to this Minahan-Nemeshansky superconformal field theories of type E678 of Argyres. Okay, so and the nice feature is that the deformation parameters of the integrable systems are they match precisely the mass parameters of SPOT in a natural way. So mostly today I will talk about rank 1 case when the abelian variety is just elliptic curve and the group is just group of roots of unity. Okay, so let me just.
Can I ask a question about the USP2N theory? Is the theory with an adjoint hyper?
Philip, maybe you can.
No, it's the one with 4 fundamentals and an anti-symmetric, a kind of a tracelet.
Okay. So that's not the okay.
Yeah. So it's the generalization of the SU2 NF equals 4 theory to higher.
Okay. So in terms of classes, it's really you're always on a sphere. You don't want to be on a torus.
Correct, I think.
Okay.
Right. Thanks. And so elliptic curves with symmetries, as I said, there are only 4 cases, and because this is Quiver Meeting, probably at least yes, it's a good point to show some quivers. So the elliptic curves with symmetries secretly actually correspond to fine Dynkin quivers of star-shaped form, and here they are, and so Alistair King, with colleague, the colleague and friend, he refers to this as 3 musketeers. I like this name because it's actually, yes, it's actually 4. Yes, and so let's do some numerology. So if you, so what the numbers which I put here below are the leg lengths of this quiver. So I just there is one central node. These are star-shaped, and I count the lengths of each leg by including the vertex, the central vertex as well. So for instance, here I have 1, 2, 3. So all 3 legs have length 3. For E7, it's 4, 4, 2. And here we have 6 and 3 and 2. So these numbers are just leg lengths. On the other hand, here are elliptic curves with symmetry. So in this case, when elliptic curve with Z2 symmetry, it could be arbitrary. It just the Z2 symmetry just Z goes to negative Z. And so any elliptic curve appears here. In this case, we need the elliptic curve with the lattice of periods being hexagonal, and the same here. So these cases allow symmetry for the 3 or 6, and the elliptic curve with symmetry Z4 symmetry has to be rectangular. The lattice has to be the square lattice, and so tau should be I. And in each case, what you can do, you can remember we need to eventually look at the quotient by the group. But if you take the quotient of the elliptic curve by the action of the roots of unity, you always get a Riemann sphere. You always get a P1, but it will be orbifolded at 3 or 4 points. So, and if you look at each of these orbifold points and look at the order of this of local symmetry, then you get the same numbers which appear here. Okay, so for example, when you take a quotient of elliptic curve by Z6, you have 3 fixed points, but with local symmetry, a group being Z6, Z3, and Z2. Okay, and yes, here's actually a picture illustrating this, and that's just for illustration. That's M equals 2 case. You take a quotient by Z2, so you consider among all elliptic functions you consider those which are symmetric under this D2 action. So there is only one P function, any rational function of P function. And so that's a natural coordinate on the quotient on P1. And you have 4 fixed points indicated here in different color, and they all have stabilizer Z2. And here is more complicated case. M6 has 1, 2, 3, 6 fixed points. But if you think about W orbits of these fixed points, then there is one orbit yellow, there is one orbit green of 3 points, and there is a red one with 2 points in the orbit, and the stabilizers are Z6 and Z2, and the coordinate, natural coordinate on the Riemann sphere here is just, again, you need to find a function, elliptic function, which has Z6 symmetry, and in this case, it's just P cube, which does the job. And these 3 punctures, E0, E1, E2, are just values of that function at these 3 orbits. Okay. Yes. All right. Now we need to consider Cherednik algebras for this data. So let me just give you some general background. I will be really rather vague. So in general, these Cherednik algebras go back to Cherednik, but in this geometric setting, sometimes they're called global Cherednik algebras. They were introduced by Etingof in 2004. So in the following situation, any smooth manifold, a complex manifold of dimension n with finite group acting on it, and then you can construct this Cherednik algebra H corresponding to this pair. It will have some parameters, which I indicate here as C. It's not just one parameter, family. And the spherical subalgebra is a certain subalgebra of this Cherednik algebra. And what is relevant for us is that this, so this is in the classical case. There is also quantum version. So in the classical case, these algebras are deformations of the following things. So maybe I'll start with the spherical subalgebra first. This one is a deformation of the function of the orbifold, which has been mentioned already. So you take the sheaf of functions on this orbifold, or in other words, just the W invariant part of the sheaf of functions on the cotangent bundle to X. And the Cherednik algebra itself is more kind of has more non-commutative. Yes, this one is commutative, but this one is not, because it's a semi-direct product with the group W. So this one deforms this, and so roughly you can think of BC as kind of invariant subalgebra sitting inside this one. Okay, and yes, so that's a general kind of background. Maybe one example to make it maybe more kind of concrete. Let's just take simple example. When you have just a complex line and roots of unity acting on the complex line, then you extend this action of W to the action on the cotangent bundle to your complex plane line by the roots of unity, and roots of unity acting in this way. And so this is if you take the quotient by this group action, it's C2 quotient by this section of ZM. It's the one of the Kleinian singularities of type A, and so it can be described like this as a quotient of the polynomial ring in 3 variables by one relation. And deformation, which in this case, this spherical subalgebra, spherical Cherednik subalgebra, will look like this. So instead of this relation, you will have relation where v to m is replaced by arbitrary polynomial of degree m. And so this is actually a Poisson deformation. There is a natural Poisson bracket here, and the number of parameters are just the coefficients of this polynomial, and by simple changes variables, you can make one coefficient to be 0. So that's why it's actually m minus 1 parameters rather than m. And so that's the simplest case of this Cherednik algebra for this variety. It's not elliptic curve yet, but we'll move to that later. So our case is this. Yes, we take instead cotangent bundle to elliptic curve, take quotient by Zm, and there will be again certain deformation of the orbifold, which is spherical Cherednik algebra.
So should I think of this BC as a family, or is it really just a generic value of the mass parameter?
So this BC,
yeah. So
C indicates here all these mass parameters.
Oh, C. Okay, so it's a family. Yeah. Okay, thank you.
Yeah, it's a family. Yes. So yes. So how many parameters you have? You can understand it intuitively as follows. So because it has orbifold singularities at the fixed points of the group action, when so the fixed points on the elliptic curve, and it should be 0 in the cotangent direction. That these are all possible fixed points. And remember, so locally this singularity looks like a type A singularity with the M corresponding to the local symmetry group Mi. So and therefore I told you that there is m minus 1 parameter of deformation. So therefore you need to take the sum of these numbers for the fixed points. And so remember that and these MIs were local symmetries of these 3 orbifold points. They were listed before, and you just take the sum of these numbers m minus 1 over this. So here, because of you have four twos, you subtract 1, so you get 1 deformation parameter at every orbifold point. So 4 parameters of deformation here, 6. Here you have 3 plus 3 plus 1, 7, 8 here. Okay, so the number of deformation parameters is the same as this the rank of the quiver, the specified quiver. Remember, this was D4, D6, D7, D8. And yes, okay. So in general, this is a sheaf of algebras over this quotient of x by w. So this means it's you can think of this as a family on X. So you take any open W invariant subset of X, and to such you associate algebra of sections on this set. And so yes, and once again, I'm not given the full definition of this sheaf, but just to say that it's a sheaf of algebra. So you get different algebras choosing different this open W invariant subset. So the smaller this U is, the more sections you can expect. So, but the integrable system which we look at corresponds actually to the global sections of this sheaf. And the theorem by Etingof and al. says that the algebra of global sections of this sheaf is just the free polynomial algebra generated by m elements, and these are exactly the Hamiltonians. This will be Poisson commuting elements, the Hamiltonians of that integrable system. Okay, so each of these Hamiltonians will have the leading I already told you before. The leading term is a W invariant polynomial in momentum. Now, when you have rank 1 case like here, when our x is just elliptic curve, then n is 1, and so you expect just the algebra of global sections is just polynomials of one function h, and this will have leading term being the polynomial invariant under the roots of unity, so p to m plus x to bits. So it's a ZM invariant Hamiltonian. That's our situation, just one Hamiltonian. And here is one example. When m is 2, this Hamiltonian looks like this. So it has 4 parameters, like mass parameters appearing here in front of p function. And extra parameter is the modular parameter of the underlying elliptic curve. M equals 3 is a bit more complicated, but not too bad. So it looks like that, cubic momenta, and 1, 2, 3, 4, 5, 6 parameters. And but other two cases are more complicated, and they have 6 or 7 mass parameters in that case. Okay, and
can I ask a question about this?
Yeah.
So the first example you showed with the deformation of C2 mod Zn, you could write an algebraic equation and then deform it with some parameters.
Yeah.
So here you could do the same by writing the some algebraic equation that the Weierstrass function satisfies, and then I guess here to be the square or something. For the, let's say, the m equal 2 case, can you write an equation and then see that there are 4 deformation parameters?
So it's I don't know how easy it is to see from equation. In some of the cases it might be more difficult, I think. In that case, probably you can just you get equation like y squared.
Yeah, some kind of Weierstrass form, but okay,
yes,
because
you
of
can guess. Yes, you can guess that you can introduce extra terms as deformation. Yes, in this case, it's straightforward to do it like that, but I don't think that it is not so straightforward in these cases, for example.
Okay.
So in the original Minahan-Nemeshansky papers, which corresponded to the rank 1 cases like this, that's actually how they did it. They wrote down the Weierstrass form and then asked what are all the, and tried to write down the most general complex deformation.
And they do find 7 and 8.
Yes, absolutely. Yeah.
Okay. Cool.
But here the difference with their approach is that in this case our curves will not be in Weierstrass form, but and that's why the equation are kind of more complicated. But on the other hand, some other stuff gets much simpler than in Minahan-Nemeshansky.
I see. Okay.
So yes. So let me see. I don't have much time to. Yes. Okay. So maybe I'll say a little bit about a few words about the classical dynamics. So although for physics, for string theory, as far as I understand, the dynamics, the particle dynamics here are not so relevant, maybe, but nevertheless, we will see some interesting duality here. And so the beginning is the usual classical mechanics. You have one function of P and Q in this case, just one degree of freedom for your particle, one-dimensional motion, and these are just equations of motion coming from Jacobi. And the crucial point is that they admit Lux presentation, and this Lux matrix will have a spectral parameter. So this will be M by M Lux matrix, and here is explicit formula, but I'm not requiring it. I'm not asking you to follow this in detail. It's a bit complicated. So just remember that it's M by M. So if M, for example, 6, it's 6 by 6 matrix, and these elements here of diagonal elements depend on positions only and the spectral parameter alpha. And these guys are a bit complicated. So I think I will not spend much time explaining the formula. So there is a kind of combination of elliptic functions. So this phi is one of the common combinations of sigma function, which appears usually quite often in theory of elliptic functions. And it's a complicated sum of fixed points of the action. There are parameters of deformation, which appear as coefficients here. And just to say that it's rather complicated. Okay, so it's not so simple formula, but nevertheless, the claim is that under the time flow, this Lux matrix undergoes as a spectral deformation. So the spectral curve which you associate to that is just this characteristic polynomial by this matrix, and then it doesn't change with time. So this is the object of interest from the integrable point of system point of view. That's like conservation laws for your dynamics. And this so this characteristic polynomial will be of order m because it's m by m matrix, and that's our spectral curve, which actually will be this Seiberg Witten spectral curve for the relevant SQT, but calculating this spectral curve directly is a bit daunting because it's imagine 6 by 6 matrix and very complicated elliptic functions there, and but actually the answer is quite nice, and it looks as follows. So there is a certain duality for these functions v, which I can mention only briefly. So this duality acts on these mass parameters or coupling parameters, as I call them. So changing C to what I call C check. And for example, in this m equals 2 case, with these 4 mass parameters, the transition to the dual parameters is given by this 4 by 4 matrix here. And on M is 3, you have 6 parameters, and there is some formula for the transformation and some similar formula for other cases. So it's a bit complicated, but there is this involution on from C to C check on the mass parameters, and then the Lux matrix has a curious this duality property. So it's so what I introduce here, I introduce L is our original Lux matrix, which depended on the dynamical parameters P and Q and the spectral parameter alpha. Then I introduced dual one, which looks pretty much similar, but I replace P and Q with on the spectral side with K and alpha. And there is some, okay, I will not bore you with details, but roughly there is a relation like that because it's conjugation by some matrix. It links actually characteristic polynomial of L check and of L, and as a result, what you get as an answer using this duality, you can get the answer in the following form. So this spectral curve looks like this. So this is our Hamiltonian, original Hamiltonian, remember, which we had somewhere before, like this function of P and Q, and here is a dual one in the spectral variables K and alpha, and when you change coupling mass parameters to the dual parameters C check. Okay, so the spectral curves, when you fix the value of the Hamiltonian to some z, then this is a spectral, what we call a spectral curve for this integral system. And this is like integral of motion; it doesn't change under the dynamic of the integral system. It only depends on the value of the Hamiltonian. And so these are level sets of these functions h check. So you get the foliation by this, and that's these level sets will be of high genus, m squared plus 1 in general, but remember, we need to eventually go into the quotient. So when you take the quotient by Zm, then you get actually the foliation by elliptic curves, by genus 1 curves. So that's how you get to this elliptic fibration, which we eventually want to see, right? So you get elliptic fibration by first looking at this one, and then take a quotient by Zm. And the dynamic of the integrable systems actually becomes just linear dynamics along these fibers, elliptic curves. And yes, okay, maybe I'll show it. Yes.
Could I make a comment about this interesting duality on the mass parameters? Maybe you could go back to that. There you go. I mean, in the m=2 case, which was the one where the theory had SO8 has 4 mass parameters, and the SO8 or D4 global symmetry, this duality transformation on the mass parameters was related to an outer automorphism, an action of one of the outer automorphisms of D4, and as Oleg was saying, this is kind of recognizing it really makes writing down the curves, if you like, relatively simple. But the analog here in the m=3 case he shows, that would be, from the physics point of view, you would say there's an E6 global symmetry, and it's unclear what this duality transformation on the mass parameters corresponds to from that point of view. So it's kind of,
I think I expect that this is related actually if you instead of if you move from the Higgs bundles to local systems, by changing complex structure in the modular space, then there is action of E of the corresponding while group on the what they call reflection factors on this on the local system, and there is a thing which is called reflection with respect to the central node of the quiver is what is called Katz's middle convolution, and so this is not exactly that, but it's related. It's not exactly Katz's middle convolution, but it's related. It's some of this composition of some of these reflection factors on the which represent the action of the while group on the modular space of local systems. So actually this one, if I remember correctly, the outer, you mentioned the one which is outer automorphism. I think that one has it twisted a little bit, tweaked a little bit, so it has minuses in slightly different place. So it's still an involution, but this one in exactly this form, I think it's actually, in this case, it will be exactly the reflection with respect to the central node. So it will be just this Katz's middle convolution, which is kind of well known in Penlever theory, and so this should be of similar nature, I think.
Okay, thanks.
But we haven't checked yet exact relation. Yes, so this one, for example, it has actually 3 eigenvalues equal to -1. So it's not just a simple reflection. It's involution, but not a reflection. Yes. So. Yes, so we have, and this duality actually allows us to see two elliptic vibrations. So one is in the original dynamical space PQ variables here, and this is on the spectral side in K alpha coordinates, and the claim is that actually the fibers in general are isomorphic as elliptic curves, and it's not quite obvious, but one should be able to see that from that action of while group on the modular space of local systems, I guess. So Okay, so there is some duality of two elliptic fibrations here, and it doesn't seem to be something very kind of classically known from the theory of elliptic pencils. So it's a bit puzzling, but right. Okay, so but the claim is that when you look at these elliptic fibrations and write them, so they were fibrations on this cotangent bundle, but eventually we want to descend onto the quotient by the group, so you need to write them in ZM invariant coordinates. So not just here, but on quotient by ZM. And then the result is that what you get is certain elliptic pencils in P2, but these pencils are not in Weierstrass form. So, but they have a nice geometric interpretation. So these pencils look like okay. So I will show just pictures without writing formulas. M equals 3 case, for example, which is E6 Minahan-Mishansky theory. So in this case, you take 3 lines in the on the projected plane intersecting at one point, and then you choose 3 base points here and three points on each of the lines. So together you have 9 points. You choose them. If you choose them arbitrarily, then there will be only one cubic curve through these 9 points, and that will be just the reducible curve given by the product of these 3 lines. But if you impose one constraint on these 9 points, then you would have actually one-dimensional pencil of elliptic curves passing through these points. So pencil of cubic curves through these points exists if these points are not in generic position, and then the pencil is just like that. So you need to find another elliptic curve passing through these 9 points. It's not too difficult to calculate, and so the parameters, the mass parameters, corresponds to the positions basically of these 9 points. So you might think that there are 9 parameters, but actually there are 6 for the following reason. So first, there is one overall constraint for the 9 points to allow a pencil. So it removes one parameter out of 9, so you get 8. And then there is a 2-parameter family of transformations on the projective plane which fix this triple of lines. So with this 2-dimensional family of transformation, you can get rid of 2 further parameters, so you end up with 6. So and the pencils for other 2 cases look nice as well. So this one is a kind of very classically very well-known pencil of cubics with 9 base points, just specifically located in this case. And for M equals 4, you have a picture like this. Again, you have 3 lines in P2, and you choose 4 points here, 4 points here, and the further 2 points, P9, P10, and requirement is that the curve should have degree 4, so polynomial of degree 4 in homogeneous coordinates on the projective plane, which should pass through all 10 points with condition that actually these 2 points are ordinary double points, are indicated by this little crosses. So the quartic, so your quartic curve should have two double points, and these are actually if you look for quartic curves of genus 1, which have geometric genus 1, these are exactly quartics with 2 double points. So that's the the pencils of quartics of genus 1 appear here. Okay, so a similar consideration shows that there are 7 parameters here, and then you can write down explicit formulas. And M equals 6 gives the following pencil. So you have 6 points on one line, three double points, ordinary double points here, and 3 points, ordinary triple points P10, 11. So now you look for curves of degree 6, sextics, which should have ordinary double points here and ordinary triple points there, and passing through all. And this is a parametric family, and when you fix these 8 parameters, then it's just a one-dimensional family of elliptic curves of degree 6, and the coordinate on this pencil is the Coulomb parameter in terms of physics. Coordinate on the Coulomb branch. And, okay, I'll skip m equals 2. It's a better known case. And I don't have time to talk about quantum spectral curves.
Can I ask a question just about the previous thing?
Yeah.
Yeah, sorry, or before. So this point, so it's all in P2, right? All these points, they are in P2?
Well, in this case, it's more natural to work in the weighted projective plane. So you assign these weights. So y will have weight 2. So the equation quadratic in y and degree 4 in other variables.
Okay, but on the previous cases for E6, E7, E8, this was in.
It was just P2. So you'll P2 homogeneous coordinates.
For instance, here, what's the physical meaning of the position of these points?
Right. Oh, a good question. Yes. So you can bring this. One of the line typically you can bring to infinity, like your infinite line in P2. So you can normalize position. I mean, you can, using these projective transformations, you can bring this to your favorite maybe form, and then maybe I use pen rather than pointer, and so line. This is L0, L1, L2. L0 would be something like X W equals 0, so it's homogeneous coordinates X, Y, W. So this is infinite line at infinity, and this would be like X.
But so to do this, you have to pick, so all your points P1 to P6, you put them at infinity. You put them at W equals 0.
No. Yes, they're at infinity, but their positions are so P1 and P6. So P1 would be
different X and Y's.
They have 0 at the last place, but they still have something.
Sure. Yeah.
Yeah.
So you say that you can always, but you cannot take arbitrary 6 points and make a transformation that puts all of them at infinity. Can you do this?
Oh no! Here I use just linear transformation, not birational transformation. So there is no blow up, blow down, right? So 6 points, they're distinct. They will be at infinity, but they're distinct, right? So this so the positions of these 6 points at this infinite line is described by these 6 parameters, which I call here alpha. So this will be 6 of the, and you can, by using some freedom, you can achieve that this sum of these alphas is 0. So effectively, you have 6 parameters, sum is 0, so 5, effectively 5. So these are linear masses corresponding to this line, and there are linear masses corresponding to positions of this point. So physical parameters are literally just correspond to just geometric positions of these points. So mass 0 limit would make all them somehow all them to collide. I mean, this in the mass 0 limit, these 3 double points should collide.
I see. So each line you send to infinity in one direction. So like L0 is W equals 0, L1 is.
So if in non-homogeneous coordinates, it's very simple. So L1 is just x equals E1. L2 is just x equals E2. You can make E1 0. You can make E2 1, for example, using tremendous transformations. So, but the third line is at infinity. So it's, but again, you can move it to a finite position. If you wish, you can make L0 also, x equals E0. And so these are like 3 vertical lines, and positions of these points of the base of the pencil on these lines just corresponds to the
okay. And then you look through to all the degree 6 curves through all these points, and that depends on the masses. Okay.
Yeah.
Thank you.
Yeah. There will be one extra parameter in the family of the curves, and that's Coulomb branch.
Okay.
Coulomb branch, yes. Yes, all I can tell you at the end is that in the higher rank, we have a description which is which has the same kind of flavor. So here yes, I'll just show you the picture at the end. So in the higher rank case, what you want to achieve at the end is you want to have an n-parametric n-parametric family of curves of genus n, and then the Jacobians of these curves will give a Lagrangian fibration over the Hitchin base. So that's the picture we're aiming at, and so the main thing here is this to find this family of spectral curves, this n-parametric family of Seiberg Witten curves. That's what we want to get, and here is the answer how it looks like in geometric terms for m equals 4 case. So you remember before we had 4 points P1, P2, P3, P4, and so on. And what happens here that now you have one extra point which I call P0 here, and you consider a pencil of curves of degree 4n in this case, and they should pass through these points in the following manner. So multiplicity of P2 and so on, all these points on these lines will be n. This P1 has multiplicity n minus 1, so it's like one copy of P1 splits away. Okay, and so this antisymmetric mass parameter, it's exactly that's what's deforming positions of these points here. While this P8 up to P5 up to P8, they have to be multiplicity n, and this one, which previously in the rank 1 were double points, now becomes points of ordinary points of multiplicity 2n. Okay, so and that's the full description. So the genus of these curves will be n automatically, and so then you will have n parameters, n-parametric family of such curves. So these n parameters are these coordinates on the Coulomb, on the Hitchin base or Coulomb branch, and yes, and the configuration depends now on 8 parameters because there is extra parameter describing position of this point P0, which splits away from those. Okay, and similar pictures in other cases. So this is linked to Hitchin system. I just mentioned briefly. So that's why that's one way of confirming that this matches the Nahan-Nemeshansky theory, because these are, as I was told, these are kind of S theories of class S or S class theories. So they meet descriptions Hitchin systems, and we can get from integrable system to the same description as Hitchin system. So it's a Hitchin system, a weakly parabolic on the punctured Riemann sphere, with the group being GLMN. So here I'm talking just about these 3 cases: 3 punctures and the residue, and the parabolic data for the punctures which I call here residue pattern of punctures. It's the pattern of the eigenvalues of the Higgs field of the residue of Higgs. Higgs field has a simple pole at each of these, and the eigenvalues of this residue will have certain multiplicities. Okay, so m equals 3. The picture you have is like this. So it says that there is one eigenvalue multiplicity n, another multiplicity n minus 1, and one eigenvalue. So it's which is separate from that. So it's it matches exactly that geometric picture, which we here it's a different case, but when you have n minus 1 and 1. M equals 4 is, yes, exactly the case pictured on the previous slide. And so the pattern, the parabolic data, or the pattern of the residues at the punctures of this Riemann sphere will have the following shape. And when n is 6, you get this description. So if this antisymmetric mass goes to 0, this splitting disappears, and you get just n here instead of n minus 1 and 1. And then your spectral curves actually become just reducible. They become products of n copies of rank 1 curve. So that's degeneration happening in that case. But the anti-symmetric mass, what it does, it just splits one of the eigenvalues in this way. Okay, so that's all. Thank you very much.
All right, let's thank Oleg.
Thanks.
Do we have questions?
Can ask another question.
Yes.
So does this pattern generalize? Like if I take a P1, but I put some number of punctures like here, but some others and some other partitions like this, then can I associate to it this space of curves of certain genus that go through a number of points, like the picture you were showing before? Is it
so,
some,
in general, it might not be that simple.
Mm-hmm.
So, of course, you can consider Hitchin systems of all possible types. You can fix arbitrary parabolic data at the punctures, and then you can calculate what will be the genus of the spectral curves. And so here, what is special is that these are Hitchin systems which come from this elliptic integral system.
Mm.
So we kind of work from the other end. We have these integral systems at our disposal, and then we want to interpret them as Hitchin systems, and we come to this pattern. So for other elliptic systems in this family, these Calogero Moser systems, the situation might be a little bit more complicated. So what happened here? The mass parameters basically were all the parameters you need to describe this pattern of the eigenvalues, right? So you need 2 parameters describing this eigenvalue, 1 more here, so 4 parameters here, 3 parameters here, and 3 parameters here. Plus there is a freedom which you can use to reduce the number of parameters. What may happen, and I think happens for other elliptic integrable systems in this family sometimes, is that in addition to the pattern of residues which you have, you might also need to impose. So your mass parameters you will have fewer mass parameters than the pattern allows. So which means that there would be some extra relations between some of these eigenvalues.
Okay.
So,
yes, I see. Thank you.
So it could be more subtle than that. Yes, and I think I saw a recent paper of the Argyres courses when they actually look at these Hitchin systems with punctures, and they really observe some cases when you need relations between residues at different, at different punctures and to be imposed.
Okay.
So, I mean, it's not, is it clear that all of these crystallographic elliptic Calogero Moser systems can be recast as Hitchin systems, or is it just something that's been shown on for some cases?
It's not obvious. And so we see this in these cases. I expect it can be done, going through cases. And so that's the plan, actually, right? And remember, some of these integrable systems include usual elliptic Calogero Moser systems related to different root systems, just usual root systems. And some of those, in general, they are not known. There is no nice interpretation for them in the literature as Hitchin systems.
Mm-hmm.
So we might have something to say about those as well, maybe. But like type A Calogero Moser system can be interpreted as Hitchin system on the torus, not on the Riemann sphere, right? So sometimes reduction to Riemann sphere happens because of some extra symmetries in the integral system. So I expect in many cases it would still work, and we'll get three-punctured Riemann sphere in many cases for this exceptional, not as exceptional, but these families of complex reflection groups. But to see this link is it's not obvious to me. We need to, starting from the integral system, you need to really work out what are the poles of the Lux matrix, what are the residues, what is the pattern there, and we look briefly, for example, for G2 case, and already there you see that there is something more subtle going on, that you will have 4 punctures, but you will have, as I said, you will have some relation between residues at different punctures. So it's no, I wouldn't say that this is clear.
Thanks.
Of course, philosophically, people believe that any nice integrable system eventually can be interpreted as a Hitchin system. So from that point of view, yes, but if you want to make it concrete, then it's not so.
Okay, very nice. Do we have more questions? Well, if not, then I would suggest we thank Oleg again.
Thank you.
And we can go off the record.